Okay, so in this video, we're going to move on to the final section of this unit. And before we do so, I want you to try to answer these two questions. Okay, so think about the moon in orbit around the Earth, um, moving in a mostly circular orbit. We'll talk more about the actual shape of the orbit later. But based off of what we've been talking about so far in this unit, what is required for the moon to orbit around the Earth in a circular orbit? Okay, well, it's not really going to be that much of a surprise, but the answer to that question is centripetal force. Okay, in order for any object to move in circular motion, there is a centripetal force that is required, which is what we've been talking about. And I kind of give it away in the next question as well. What force do you think provides the centripetal force in order for the moon to orbit the Earth? Okay, so see if you can figure that out. And again, hopefully this is not too much of a surprise, but the answer to the last question is gravity. Okay, it is the gravitational force which provides the centripetal force in order for the moon to orbit the Earth. And in fact, the Earth to orbit the sun, the solar system to orbit around the galaxy, and so on, all those orbits are due to the gravitational force. And that the answer to that might seem really obvious, but it wasn't always so obvious. And so going back to the time of Newton, a lot of people, for whatever reason, are taught that, Newton discovered gravity or something like that. Apple falls on his head, he discovers gravity. Okay, that's definitely not true. People, I don't know if the Apple story is true. That may or may not be true. But people knew about gravity, of course. I mean, things have been falling for thousands of years. Okay, Newton didn't discover gravity. Okay, here's what Newton did in relation to gravity. Back then, people were trying to figure out what force was it causing the orbits, okay? And some people thought maybe it's magnetism. Maybe there's like iron in the earth and it's like a magnetic force that makes the earth move in circular motion. Or, maybe there's like invisible strings providing the centripetal force. Newton realized that the force responsible for the moon orbiting the earth is the same force responsible for the apple falling towards the ground, and that force is gravity. Okay, and so Newton's contribution wasn't to, discover gravity that people knew about, but it was to recognize that it was gravity providing the centripetal force for that type of circular motion of orbits. Okay, and so we know about Newton's three laws, of course, we learned about that last semester. Okay, so now we're going to learn about his so-called fourth law, and that is what's called Newton's universal law of gravitation. Okay, and so this is going to be an equation. Newton's law of gravitation is an equation. The word universal in this law brings forth the idea that this equation works everywhere in the universe. And so one of the big things that Newton came up with is this idea that the laws of physics on Earth are the same as the laws of physics elsewhere in the universe. Okay, and at the time that was kind of a controversial idea, but now we accept that. Okay, so that's what's the universal law of gravitation. And so we'll talk more about this equation momentarily. But basically, under Newton's law of universal gravitation, the idea is that all objects which have mass attract all other objects which have mass with a gravitational force. Now, all means all. Every object in the universe, if it has mass, okay, that is the important quantity, attracts, okay, that means pulls towards all other objects that have mass with a gravitational force. Okay, so there's a gravitational force between you and the person next to you. Okay, there's a gravitational force between your cell phone and your head. Okay, you might not notice it because it's so small, but it is in fact there. Okay, you can calculate it, you can measure it. And so normally we only measure, or we only notice gravitational force when there's very big masses involved. So for example, the Earth has a lot of mass, and so we notice when things fall towards the Earth, of course. But technically speaking, all other objects in the universe, regardless of how small they are, if they have mass, they put a gravitational force on all other objects which have mass. Now, let's look more at Newton's law of gravitation, the equation, the actual law. Okay, so Newton's law of gravitation looks something like this. Okay, so to calculate the force of gravity between two masses, we have a capital G, which is known as the gravitational constant. It has a value of approximately 6.67 times 10 to the negative 11. Okay, notice it's a very small exponent, okay, written in scientific notation. We will talk about the units of G momentarily. Next, we have the product of the two masses. And so Newton's law of gravitation allows us to calculate the gravitational force between two objects that have mass m1 and m2. Okay, so those are the masses of our objects measured in kilograms, of course. Divided by r squared. And this is where people get a little confused because we've been using r for radius everywhere up to this point in this unit. Okay, this r does not represent radius. Okay, this r is the distance between mass 1 and mass 2. Okay, unfortunately, or not, it has the same symbol as radius, but this is not radius. This r is distance. Okay, and so this equation allows us to calculate the gravitational force between any two masses as long as we know their masses and we know the distance of separation between them. Okay, now you might be saying this whole time, wait, I thought we have an equation for force of gravity. I thought Fg equals mg. Okay, so it turns out that this equation is only approximately true. Okay, it's only an approximation as long as you're close to the surface of a planet. It says to the surface of Earth, but of course this equation works as long as you're close to the surface of any object, whether it's the moon or Jupiter or whatever, as long as you know the acceleration due to gravity. And we will actually see later on this unit how to calculate the acceleration due to gravity for different planets or moons. Okay, there's a way to do that using Newton's law of gravitation. Okay, so in other words, the equation for Fg that we've been using so far this year, that's like the baby version of force of gravity. This is kind of more like the grown-up-ish version of uh, gravity, more or less. At least the version that we teach you in high school. Okay, actually a more grown-up version um, of gravity, which is called general relativity, which was discovered by Einstein. But we're not going to talk about that because that's like advanced physics right there. Okay, so this is Newton's universal law of gravitation. Now, before we get into dissecting this equation, seeing what we can do with it, I want to take a moment and I want us to figure out what are the units for G. Okay, and so I'll tell you right now, knowing the units for G by itself, that's not that crucial. Okay, but the purpose of us doing this is to teach you a skill, and the skill is to be able to determine the units for a constant based off of the equation. Okay, because sometimes you're asked to do that by the IB. Okay, so it's not so important that you know the units for G. To be honest, I don't have them memorized, and if I want to find them, I would do the trick I'm about to show you. Okay, so let's say I want to know what are the units for the gravitational constant. I know that force of gravity is a force, and so that is measured in newtons. Okay, and so I'm going to plug in newtons for Fg. Okay, these square brackets are just to indicate that's a unit. So if I want to find the units for G, basically I'm going to plug in the units for every quantity in my equation. Okay, so mass 1 is in kilograms. If you multiply mass 1 and mass 2, kilograms times kilograms gives you kilograms squared, and then divide by r squared. Okay, r, distance, is measured in meters. And now if I rearrange this equation and get G by itself, I find that G, at least the units for G, are Newton times meter squared divided by kilograms squared. Or in IB notation, you would write that with a negative exponent. So it would be Newton meters squared per kilogram squared. Okay, so G is approximately equal to 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. And so that is the value for the gravitational constant along with the correct unit. Okay, and again, the purpose of this exercise is really just to teach you the skill of how do you find the unit of something given the equation and knowing the units of everything else. Okay, and we'll see that again in the future. Okay, so pause there if you need to look at that some more. Okay, so let's break down some properties of Newton's law of gravitation. Okay, now according to Newton, the gravitational force has a few different properties. Okay, number one, it is always an attractive force. Okay, so when I say an attractive force, I mean it's always a force that pulls objects together. Now there's some forces in the universe that are repulsive, and if you've ever played with magnets, you might have felt this before. If you take two magnets, if you hold them one way, they snap together, and if you turn one of the magnets around, they kind of it feels like they push apart. Okay, some forces can be attractive or repulsive. Gravity is only an attractive force. Okay, so gravity always pulls things together. Next, the force between two objects gets weaker as the distance between the objects gets smaller. And that should be immediately obvious looking at Newton's law of gravitation because you have g m1 m2 divided by r squared. R is the distance between the two masses. And so clearly, actually this is a mistake. The force between two objects gets weaker. It should say as the distance gets larger. Okay, sorry, that was definitely a mistake. Okay, the force between two objects gets weaker as the distance between the objects gets larger. Because if you're dividing by a bigger value, you should get a smaller force. Okay, so the bigger R is, the smaller Fg is. Okay, that's just, obvious from the equation. And then finally, the force between two objects gets stronger as the mass of either object gets larger. And again, that's self-evident just looking at the equation. Clearly, if you make m1 or m2 bigger, if you multiply a bigger number, if you multiply by a bigger number, you get a bigger force. And again, that's just kind of obvious from the equation. Okay, so keeping those in mind, let's do some examples with calculations. Okay, so let's say we want to find the force of gravity between a boy and a girl, and we have a boy, normal sized boy, 165 pounds. I have converted that to kilograms for you because we do have to be in kilograms for calculations. And the boy sitting next to a girl, she weighs about 110 pounds, so that represents a mass of about 50 kilograms. And they're pretty close together, they're about half a meter apart. So let's see what the calculation looks like for the gravitational force between them. All right, so we have Newton's law of gravitation, Fg equals g m1 m2 divided by r squared. And this is just a very straightforward calculation. All we're doing here is we're plugging numbers into a calculator. Okay, so we have 6.67 times 10 to the negative 11. That's the gravitational constant. Mass 1, it honestly doesn't matter which mass is mass 1 and which mass is mass 2. And the reason it doesn't matter, by the way, is because the force of gravity on the boy and the force of gravity on the girl are the same because of Newton's third law. Okay, so the boy pulls on the girl pulls back on the boy, and so it doesn't really matter which one is mass 1 or which one is mass 2. Okay, but let's say the boy is mass 1 and the girl is mass 2, and then we divide by the distance between them squared. Okay, make sure you don't forget to square the distance between them. Okay, so I'm typing this into my calculator. Okay, and so I'm just having some trouble loading my calculator. There we go. Okay, so 74.8 times 50 divided by 0.5 squared, and I get 9.98 times 10 to the negative 7 newtons. That is a very, 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 very small force. Okay, just to give you an idea, if you imagine like how much force it takes to lift an apple, that's about 1 newton. Okay, this is like, literally like a million times less than that. Okay, literally about a million because it's about 6 orders of magnitude less than the weight of an apple. Okay, does this gravitational force exist? Yes. Can we calculate it? Yes. Can we measure it? Depending on what the objects are, you can do very sensitive experiments with masses, and they've been done over many years just to confirm Newton's law of gravitation works. But it's very difficult to measure with small masses. Okay, so it can be done, but it's really hard to do outside of a lab setting. So why don't we notice this gravitational force normally? Well, because it's really small. Okay, it's so small, you almost don't even notice it unless the masses are really big or the distance is really small. Okay, or both. That's why typically, even though there is a gravitational attraction between the boy and the girl, it's dominated by the gravitational attraction from the Earth. Okay, so the Earth has so much more mass that you notice the force of gravity from the Earth more than you notice the force of gravity from everything around you. Okay, even though those forces do exist. Okay, so pause there if you need to look at that some more. Okay, example 2. This is another one of those proportional reasoning questions, and you will see more and more questions like this as we go along in IB physics. Okay, but this question says two objects, each with mass m, are separated by a distance r. The gravitational force between the masses is measured to be Fg. Right, which makes sense because we have Newton's law of gravitation. By the way, this type of proportional reasoning question is also something we do in on-level physics, and so it's not a super complicated type of question as long as you understand how to approach it. The question says state in terms of Fg the gravitational force that would act between the two objects if the distance between them doubled. So when you have a proportional reasoning question, you're basically changing one variable and saying how does another variable change. When it says state in terms of Fg, okay, that means our answer to this question should be a multiple of Fg. So the change we're making is we are making r into 2r because we're doubling the distance between the two objects. So I want to find a new force of gravity, Fg prime, and so I'm going to do that by making the substitution that they tell us to make. Okay, so instead of r squared, it's going to be 2r squared. Okay, the square has to go outside the parentheses. That's very important. And so what you get is 2 squared is 4, r squared is r squared, so you get 4r squared. If you compare this to our original answer, notice that they are basically the exact same, except that the one on the right is 4 times smaller because there's 4 in the bottom. Okay, so the answer to the question is that Fg prime is equal to 1/4 times Fg. Okay, so this is very common to see this type of question as like a multiple choice question. So either the answer would be like 1/4 Fg or it'd be Fg over 4, either way. Okay, so that's just a basic proportional reasoning question using Newton's law of gravitation. Okay, so pause there if you need to look at that some more. Okay, and so hopefully you've noticed that when you're doing calculations with Newton's law of gravitation, because the gravitational constant is so small, it's like times 10 to the negative 11, the only time you actually really notice the force of gravity is if the masses are very big. Okay, it turns out the force of gravity is actually one of the weakest forces in the universe. It really, really only dominates when the masses are ginormous, like the mass of a star, or the mass of a planet, or the mass of a galaxy. Okay, so on a big scale, gravity matters. On a very small scale, gravity is like literally one of the weakest forces in the universe. Okay, so let's do one more example, just kind of conceptually. Based off of what we've talked about so far in this video, I want you to try and answer these last two questions on your own. Okay, how does the gravitational force on a rocket ship change as a rocket flies higher up into the sky? Okay, and so the answer to that question is, let's see if we can write this in complete sentences. The way I would write that is I would start by saying the gravitational force on a rocket ship, writing in complete sentences. I want to kind of repeat the question. Um, and it actually decreases as the rocket flies higher into the sky. Here, when you're thinking about the gravitational force, you're talking about the two masses being the rocket ship and the Earth. The higher up you go into the air, the greater the distance between the rocket ship and the Earth. So the gravitational force on a rocket ship decreases as it flies higher into the sky. Now, what about the second question? How would the gravitational force on a rocket change if its mass decreased? Okay, so try to answer that one. Okay, and this one actually has the same answer. The gravitational force on a rocket ship decreases as the rocket loses mass. And again, that's a straight consequence from the equation because, if you're multiplying by mass in the equation, if the mass of either object changes, then the if the mass of either object decreases and you're multiplying by a smaller number, that means you're going to get a smaller gravitational force. And you might ask, like, why would a rocket ship's mass decrease? Well, as it flies up into the air, it's losing fuel. It's burning fuel to, have enough energy to propel itself up into the air. Okay, so rocket blasting off from the ground is actually the gravitational force on it is weakening, both because it's going farther from the Earth and also because its mass is decreasing. Okay, so just a little conceptual question there. Okay, so in this video, we talked about just the very, very basics of Newton's law of gravitation. In the next couple of videos, we're going to start doing more complicated calculations with Newton's law of gravitation. We're going to see how it relates back to centripetal force, and then we're going to talk more about how to do calculations, such as how do you find the acceleration due to gravity for a planet or a moon. Okay, so we will go ahead and stop it here. As always, please let me know if you have any questions, and I'll see you guys in the next video.